Good? Okay. Okay, well, thank you, hardcore enthusiasts, for coming back for this final lecture. There is a small reward, which is that some of the ideas I'll talk about today are accessible without understanding all the fine details, even though, as usual, fine details will be integral to the proofs. There's some really beautiful conceptual ideas, and in some sense it's these conceptual ideas which I think people have already heard, and now you'll have a chance to see the context in which they originally came up. So our theme for all of today is null geodesics and what they tell us about space-time. And we defined them last time, but let's just give you another a fresh definition. So there's an affine parameter lambda such that this is 0, but also this is any geodesic with an affine parameter, but also dx mu this is second line is the statement that it's null. And last time we discussed promptness, which is a criterion that tells us how to say one null geodesic is essentially better than another one, is sort of quicker than another one. And it's very counterintuitive in some way because all of them are null, so the actual integrated proper time is just 0. So there's no way to compare them using that. The affine parameter, of course, will take a finite value when integrated along this line, but then you can scale the affine parameter as you like. So how do you compare two different geodesics? Someone could have scaled the parameter for one of them and not the other. Promptness, on the other hand, says that if I'm starting at a point P and I want to get to a space-time point Q, which means I want to get to the spatial point Q at some given time, and supposing I do have a geodesic or any path indeed that does this job, I might be able to find another path that goes to the same spatial point but at an earlier time. So remember, this is t, that's x. And if such a path exists, so I don't know, let's call this gamma and gamma prime. If gamma prime exists, then gamma is not prompt. And so gamma is prompt if no such path that gets there earlier exists. And this is a somewhat coordinate dependent statement because we first fix our coordinates and then we simply ask whether there's a path whose endpoint is earlier than that one. And we gave arguments for two important results. One is that if a geodesic is prompt, I'll use NG for null geodesic, is non-prompt overall. Oh, sorry. Let's give you first the prompt one is prompt. It cannot be initially non-prompt. That was the statement that if I was initially non-prompt, then I strayed off the path that was going to get me to my destination earliest. And there's no way once you stray off a path like that to get back to it without going space-like. So this, of course, everything is causal here. All paths we're talking about are causal. They cannot be space-like. So in some sense, if it was initially non-prompt, it's too late for it to ever catch up. So that's one result. And the second result is if a null geodesic is non-prompt overall, it nevertheless has an initial prompt segment. So this is sort of the reverse statement. It says that if I got from P to Q too late, it might be because I was prompt for a while and then I became lazy and went non-prompt in the last part, making the whole thing non-prompt. Not just it might be, it's always the case if it's a null geodesic that initially it's prompt. It's stronger than that. And this, yes.
Does that mean something special happened along the way?
It just means that, yeah, it does in a way. So my interpretation of this is that, you know, the initials in any initial segment, you can take a small enough neighborhood that effectively behaves Minkowski by an astute choice of coordinates. And then in Minkowski, it's always true. Every null geodesic is just a straight line and it's always prompt and there's nothing to discuss. So we gave this example of gravitational lensing, which causes some geodesics from distant stars to be non-prompt by the time they reach us. And as you say, something was obviously happening. There was obviously a matter distribution that deflected them in such a way that one arrived before the other. But either a matter distribution or some topology, there should be something happening. So I think the word is, I think your words are correct. Something should happen to me. Of course, I could also just, I could just be standing there and give it a whack. That would also, I mean, that's the same thing.
But it's not necessarily specific event.
Not necessarily, no, no. It's just that there is some initial segment in which it's prompt.
And about the coordinate dependence, it's not
Yeah.
so bad having a discussion that involves a particular choice of coordinates.
Sure,
But
absolutely.
What important is that actually the overall concept is coordinate independent. Can one say that?
I think so, because I think arriving at an earlier time means basically that this past point contains in its future, light cone contains the future point. So in that sense, it's actually, it's causality dependent as it should be. It's a statement that something was in the causal past of something else. So, but as I mentioned, a colleague and I just started discussing how maybe one can make this a little more formal, and it would be nice if we could manifest it. Yeah, yeah. Now, one last result before I go on to today's material is that if I start with a point P and I consider its causal future, I'll remind you what that is. So it's called J plus of P. It's the set of points in the future that are reachable by all causal curves, and causal curves are those which are either time-like or null, never space-like. So the causal future J plus of P looks like that, and it usually has a boundary. In this case, this whole cone. And so the boundary of the causal future is called del J plus of P. So you can ask, are there prompt null geodesics from P to a point here or a point here? So this is the interior, this is the boundary. And intuitively it's clear, and again in Minkowski it's completely obvious that you can only have prompt null geodesics that reach boundary points, because that's what the light cone actually means. But it's actually true in greater generality, and so I think I stated and maybe discussed this last time. A prompt, if and only if a prompt, okay, let's just call it if a prompt null geodesic PQ exists, then Q is in the boundary of the causal future of P. Good. So this is a brief review of what I did last time. So are there any questions on this? If not, I'll move on, but please feel free. Okay, so I concluded the last lecture with a theorem with a statement that prompt is the same as achronal. So let's remind ourselves what achronal means, and then let's sketch how this is proved. So achronal means there is no time-like curve connecting any two points. So achronal refers to any set. It could be a path, as in this example, but more generally an achronal set could be just any set, and in particular Cauchy hypersurface also has to be achronal. And what it says is apparently that, well, the achronal surface should be either null or space-like, can't be time-like. But it says more than that, because it also says that there's literally no way to get by a time-like path from one point to another. And we had this helical path we gave as an example, where you can just jump to another wind of the helix by a time-like path. So then that's not achronal. I don't know if people refer to non-achronal sets as chronal, probably they do, but yeah. So this is what achronal means, and now we need to prove that prompt is the same as achronal, and we can do it by just drawing pictures. And what we'll do is we'll first assume non-achronal, and that this implies non-prompt. Then we'll assume non-prompt and show the reverse implication, and that will prove this. Probably I should. Sorry?
The Cauchy surface is achronal.
Yes, but no. So okay. So a path for a path. So it's for a one-dimensional path. So yeah. So prompt is defined only for paths. Achronal is defined more generally, but here we are using it on paths. Space-like path is not causal path. Sorry, I always forget these words. Thank you. No, it's really important. They are all sort of reasonably correct in the notes, but yeah. Okay, so let's prove this. So here's our path which is trying to be prompt. It's a candidate, but it's not achronal. So it means that from here to here, I can somehow go by a time-like path. Okay. Now, if that is so, then this segment is itself non-prompt, because a time-like path is necessarily non-prompt from here to here, whatever these 2 points are, maybe R1 and R2. Okay, so just this segment is clearly non-prompt as a path from R1 to R2, which means there must exist a path from R1 to the same spatial point as R2, which gets there sooner. So if this is R2, there must exist this path, which gets to R2 prime below R2 and therefore gets there sooner. And given that this path exists and it's a little before R2, I can continue it all the way just shadowing this. This is the shadowing argument we used before until it gets here. And the fact that this path gets to Q prime, which is earlier than Q, proves that it's non-prompt. So just having any time-like connection is enough to guarantee that my whole path is non-prompt. So non-achronal or chronal, I still don't know whether I should say that. Chronal implies, maybe I'll keep it how it was because it's the negative of the original statement. Okay, now the reverse implication, which is almost in a way simpler, non-prompt should imply non-achronal. So here I have a path which is frankly and honestly non-prompt, and that means there is another path, I already know this, that ends here. Well, now I can connect this dotted line here to make a path from P to Q prime to Q that has a prompt segment and then a time-like segment. Okay. Now we proved, or actually we stated a theorem some time ago, I think I stated it, if not it's in my notes, that given any path that's partly null and partly time-like from P to Q, I can always deform it to find a fully time-like path. And so there is actually a path obtained by deforming PQ prime Q, which looks like this and is fully time-like. This is one of those theorems that does involve a bit of topology, and so I probably didn't discuss the proof. It's involved, it's also in my notes. But it seems reasonable from the picture. And given that there's a time-like path from P to Q, we've proved that that this path is non-achronal because there is another way to get from the beginning to the end, which is time-like. So these are two results that we'll need. And one last one before we plunge in to today's main topic is an observation which I should have made a few times before, maybe I did once. We keep talking about paths from P to Q, but there's also a meaning for paths from K to Q, where K isn't a point but a set. And it could, for example, be a submanifold. It could be a Cauchy surface. It could be a lot of things. But and when it comes to examples, we'll state the properties needed for K. But right now, just imagine that K is some subset of my full manifold, of my full space-time. And there's a point Q that's inside the causal future of all of K. What's the causal future of all of K? It's just J plus of K is the union over all points in K, the causal future of that point. Just pick every point, make its light cone, take the interior and boundary, take the union over everything, and you have the causal future of the set. So there's a very straightforward generalization from causal future and past of a point to that of a set. And now I can ask for paths between K and Q where I don't specify their starting point in K. I just specify that they start in K. But for example, I can define promptness, I can define compactness, all these properties just for the space of paths that start on K and end in Q. So for example, for promptness, a path like this, which I've just drawn, starting in K and ending at Q, will be non-prompt if there's another path also starting on K, but not necessarily at the same point, but ending at a point before Q. So from the point of view of the set, the goal is to get there earlier, but we start anywhere we like. We can be anywhere in K that we like. We can be as close to Q as we can get. But then you cannot say that your path is prompt if I is starting somewhere else on K, I'm able to get there earlier. So this is the definition of promptness for paths from K to Q. Similarly, some time ago we discussed a theorem about the compactness of the space CPQ, which is the space of paths from P to Q. And basically this compactness mainly involved what was called sequential compactness, namely that if I have a sequence of paths all between P and Q, then they will converge, if they converge rather, to some path, then that path is actually in the same space, CPQ. It's also causal and it's contained in the same open set. So we can generalize this just by changing the figure a little bit to CKQ, where all these paths start not at one point P, but at possibly different points on a submanifold or a subspace, subset K, but they all end at the same point Q. So in that case, this is also compact, and the same result holds, namely if I have any family of curves from starting at k and ending at q that converges to a curve starting at k ending in q, then that convergence curve will be in my space. And we'll use that today. Good. Okay, so with all these preliminaries out of the way, let's state the single most crucial fact which everyone has known since they studied special relativity, which is that in a d-dimensional space-time, we can have always have two, space-time of course always has signature minus, plus, plus, or the other way, but important point is that there's one time. Then I can always have two null, two linearly independent null directions and d minus two space-like directions. And this is pretty obvious in even in special relativity, where we take x0 up to x d minus 1, and then we define u and v to be x0 plus xd minus 1 and x0 minus xd minus 1, and then x1 up to xd minus 2 are just space-like coordinates, while these two are null. This is strikingly different from what happens when you separate space from time. There's only one time-like direction and d minus 1 space-like directions, but there are two null directions and d minus 2 space-like directions. And this is actually a theorem, and this is true in any space-time, not just Minkowski, that if I have a d minus 2 dimensional space-like surface, it's always orthogonal to two null vectors. Okay, and what's even more interesting, if we now give these, so these are coordinates I've described, but if I have vectors, then I can give my vectors names like w mu is 1 0 1 and w prime mu is 1 0 0 minus 1. And then I have all the others, I don't know, v mu, which are, everything else is 0. So they have a 1 in various places. So these are the d minus 2 space-like ones. These are the two null vectors. And the interesting thing, which again everyone knows, is that w dot w is 0 because it's null. So is w prime dot w prime 0. But w dot w prime is not 0, even though they are visibly perpendicular on a space-time diagram. That's how the Minkowski metric works. But again, this construction, and I've explained in my notes, is much more general, and this property just holds in every space-time. There are always two null and d minus 2 space-like directions. And it's this property which spoils our ability to normalize any null vector, because obviously these being true don't help us normalize anything because the norm is 0. This being true only helps us normalize them relative to each other. You could ask for this product to be 1, but you could then scale w and w prime by equal and opposite amounts, and that's just a boost, and that just keeps the norm invariant. So that's why it's difficult to normalize, or impossible actually, to normalize null vectors, and that's why we got into this business of prompt geodesics in the first place.
You're saying something about the orthogonality property of V.
Yeah. So of course, v dot w and v dot w prime are 0.
Because otherwise,
And yeah.
if you would do that, you would have d minus 1.
If I didn't, yeah, of course. No, they wouldn't be linearly independent.
Yeah.
That's the point.
So
Yeah.
that's the point.
Yeah. Yeah. Of course. So that's exactly, yes. Now, just to get a little intuition, if this is x and this is t, of course, we've seen this a million times. So these are the w and w prime directions, or if you like, is the. Now, I constantly mix up which is my u axis and which is my v axis, but in most of my figures, u goes that way and v goes that way. The important point is that these two are back to back in space. So, for example, if I emit a pair of photons here and one goes off to plus infinity along x and the other to minus infinity along x, then these are their world lines. So, these are literally in space back to back. They don't look back to back because this is space time, not space. I hope that point is clear. Okay, and that's going to be very important. So, for example, if this point from where I emitted was on some surface like a sphere in space, then u would be the, so this is space now, not space time. So 3D Euclidean space with a two sphere embedded in it, then the u geodesic would go this way and the v would go this way, outward and inward. Okay, in that case, my coordinates are t and r, the radial coordinate. So it's just important to understand that while in space time they look like that, in ordinary space they just look outward and inward. I hope this point is clear. It confused the hell out of me for a long time until I drew enough pictures and thought about it. So we will go between these two descriptions, space and space-time, because after all, space-time is how events play out, but space is where we actually live. So yeah. So I hope this is clear. This statement that they are back to back is exactly the statement that they propagate along the radial direction to increasing R or decreasing R. Good. Okay. Now we would like a Raychaudhuri equation which tells us how geodesics focus or don't, and that's going to be the key again. So this time it's yes.
So in this space picture, U goes from 0 to infinity and V goes from 0 to infinity, the space picture.
Yes.
But in the space time, I can draw like U minus infinity to infinity. So how can
No, so actually no, I could have come in from here, so this would still be U. Not infinity maybe, but I could have come in from the, right? I could have something expanding. So for a fixed sphere, so if I create an event on the sphere like a flash, then in the future it propagates out. But that same thing in the past obviously propagates in, or in other words, it can, if I respond to a signal, that signal would have come from inside. So, so these directions are the emission directions, if you like, which means I'm going to the future, which means this. And what you were asking about are the continuations of these lines into the past. Yeah, good. Now, to set up these, so one good news is that there's almost nothing, no work to be done to derive these equations, except to set up the right congruence, as it's called, which is a set of geodesics that intersect a chosen surface. And for that, we'll first write down the appropriate synchronous coordinates. I'm not even sure this is the correct name in this case. Maybe we can call them null synchronous coordinates, because synchronous was used for the time-like case where we set G00 to be -1 and no 0 I components, and that was it. And I described in some detail how we find those coordinates. Here I'm going to write down the answer for you, and then we'll just see why this is a sensible choice of coordinates. Q depends, I think, only on yeah. This Maybe I won't write down the dependencies here, I'll write that separately. These are functions. Q, GAB is also a function, and it multiplies dxa plus ca dv dxb plus cb dv. So let me explain. What we've done is we've split our coordinates into u, v and xa, and this a index is different from the I index which runs over all of space. This runs over d minus 2 directions that are the ones orthogonal to both u and v. U and v are null. Well, u and v were null, but now I've chosen a metric where v isn't null actually. So I'll explain that. Q is a function which actually depends on v and x. GAB is a function which is an arbitrary function on the d minus 2 space-like surface, and then it's transported along the geodesics. So last time we explained how a metric that and coordinates that are defined on a surface, in that case on an initial value surface, are transported along time-like geodesics. So it's similar, and then CA are also some functions. So Q depends on V and XA, GAB depends on everything, and CA also depends on everything. Now, there would have been so first of all, let's look at a few different aspects. So there's a du dv term that's characteristic of a pair of null coordinates, but actually it's only u that's null, and that's shown by the fact that there's no du squared in the metric. So u is null. That means if I travel only along u, then the norm is 0. As far as x, these are good spatial coordinates, and the part of this metric is GAB, DXA, DXB, which is just a standard metric which I haven't specified, which is arbitrary on my d minus 2 dimensional surface. There is a coordinate freedom to choose these other components, but I could have, for example, chosen the dv term to be 0, then v would have been null. But I couldn't choose the dx dv term to be 0, so there's anyway a c. The c, if you like, gives me the cross term dx dv, and gives me the dv squared term. So I've chosen to complete the square for my convenience, and the convenience comes from the fact that if I look at the inverse metric of this metric, then GVV upper is actually equal to 0, even though GVV lower is not. And there are another few nice conditions satisfied by these inverses. And what are they? G upper UU, VV and AV are all 0. So that's the trick. What we did was to simplify the inverse metric rather than the metric, and that turns out to be a clever thing. So this is an exercise. Given this metric, invert the whole 4-dimensional metric, and you should be able to show this. And there's another nice feature which actually will come in handy. GAB is a symbol that's ambiguous. Is it the matrix inverse of G lower AB, which is a 2 by 2 matrix, or is it that I invert G mu nu, which is 4 by 4, then write G upper mu nu and then specialize to AB? As you probably know from any course in GR, these two things are not the same, but here they are the same. So is the inverse of GAB and is also G mu nu, mu equals A, mu equals B. So there are a bunch of clever things about this metric, and I think this choice of metric is due to Sachs. Sure, I think all the later developments made use of this thinking, and what basically happens is that you have two null directions to play with, but it's not always clever to take your independent coordinates to be both null. It sometimes is more clever to take one null and one not null in a useful way, and that's the way we've done here. Now, one nice confirmation that we haven't done something absurd is to count the number of functions. So, please.
So you consider to be function of p and x,
Yeah, yeah.
but I could have defined it p prime to absorb the p dependence to make this p prime and just give me function of x, and also for the CA I can get rid of the p dependence, right?
Yeah. Well, the point is that you might not easily be able to get, okay, so if you redefine only V, yeah, maybe you can actually. Yeah, I'm not sure about that. But I don't think you cannot, yeah, that's right, exactly. And you can also see that even if dv squared was absent, so this factorized form was not present, I'd still have the same number of parameters because dxa dv is not something I can make cause to vanish. So the number of parameters is this number of functions. And obviously they're not unique, no choice of metric is unique, it's just a nice choice. But if we count the number of functions, there's 1 for q, there's d minus 2, d minus 1 by 2 for GAB, and then there's D minus 2 for the CA. And I would never be able to do this live, but if you're quick. So the nice thing is that this comes out to be precisely D minus, so D minus 1 by 2. I hope this is true. And why is that good? Yes, in my notes it says it's true, so it must be true. And why is this good? Because it's the same number of functions I had in the time-like case. When I parameterized my metric to be suitable for a time-like geodesic congruence, the only function in the metric was gij, and I and j went over d minus 1 directions, so that was the number of components. Here, yeah.
G has like d into d plus 1 by 2 components,
and then subtract d, exactly right. So it must be this. So this is a confirmation that, but of course in my notes you'll find a detailed process of how to actually choose these coordinates, which is a little complicated, and I just thought it will be easier to skip it. Also, I would recommend Sachs's paper, which is very elegant, and as I said in my probably first lecture, I sort of feel sorry for him because it's really his equation, and should not therefore be called null Raychaudhuri equation. But anyway, some people call it null Raychaudhuri Sachs equation. It's also okay, I guess. Okay. Now, once we've done all this, what's the strategy? I think you know this. The strategy is to define an expansion. First, to get an identity for the Ricci tensor in terms of the 2D metric. And in the earlier case, it was the 3D metric. In principle, we'll find the Ricci tensor components in terms of Q, GAB, and CA. But this clever choice of coordinates implies that it doesn't end up depending on Q and CA, only on GAB, which is really nice. The component of interest to us, which is always the time component. So earlier it was R00, now it's RUU, because U is our null coordinate, which we are going to treat as time. And so the conclusion of a very short simple calculation is that it's minus a half del u GAB del u GAB minus a quarter GAB del u GBC GB GAC del U GBC GBD del U GAD. And if you look at this and in your mind you just replace U by 0 and AB by I and J, it looks exactly like the formula for R00 that we derived in the original Raychaudhuri equations. But it's different because now A and B always go from 1 to D minus 2. Okay, and this, as promised, shows that there's no dependence on Q and CA, though they are parameters in the metric. the Ricci tensor doesn't depend on them, and therefore we'll be able to get equations which really rely only on quantities that are determined by GAB. And we really don't care that much about Q and C. Okay. What's the quantity? Well, as always, we want to know if the determinant of this metric, which now I'm going to call capital A. Earlier I just called it det G for a 3 metric. Now I'm just going to call it capital A. And we're going to, in terms of, so we want to know whether this goes to 0, and this will be the condition for null geodesics going out of my surface to focus or not. And so the null, maybe I should start here. The null expansion I'll still use the same name theta for it, but it's del u of A upon A, and therefore it is GAB, a half GAB, comma u. Again, formulae are very, very analogous to the time-like case, and there's also a null shear which doesn't do much in our story except to provide a positive or a suitable negative term on the right side of the Raychaudhuri equation. And this is, maybe I don't have to write it. It's very similar to the previous case. And with this, just plugging those quantities into this, we immediately get the equation del u of theta plus 1 over d minus 2 theta squared is equal to minus trace of sigma squared, where sigma is the null shear, and minus 8 pi g t u. So on the way, I used the Einstein equations. But the Einstein equations, so this obviously is just r u. But why is this t? Why does it not have the trace part? Why does it not have the cosmological constant? Well, these are beautiful miracles of null coordinates, because GUU equals 0. That's exactly the statement that the u coordinate is null. And if you remember, the cosmological term in T mu nu arises with G mu nu. So T mu nu has a G mu nu lambda. So if I put mu and nu equal to 0, this term just drops out. And the same thing happens for its trace. So we just have the actual null components of the stress tensor arising in this equation. And this is the null Raychaudhuri or Sachs equation. And well, it looks exactly like the usual Raychaudhuri equation, with the only replacement that d minus 1 has become d minus 2. We also know why. But it's an illusion to think that it's telling us the same thing, because it's this is an equation for one null direction u. And what I can do now is to choose another set of coordinates in which v is null and get an equation for v as well, which obviously will be the same equation. Okay, of course it will be for a different expansion. So there will be an expansion theta for u and an expansion theta for v. So it's a new problem in that sense. There are two expansions, and this is why it's interesting. And of course we can, just to state the obvious, this means that because the right hand side now is negative, as long as T u is greater than 0, which is called the null energy condition. And it's a better energy condition than the positive energy condition. It's more likely to be satisfied, though I'm not going to go into details of it. So this, and this will tell us that theta inverse of u as is greater than theta inverse at 0. So we assume u is 0 on that d minus 2 hypersurface plus a linear term in time. And this says that all if theta inverse at u equals 0 is less than 0, all null geodesics focus in the future by a time which we can estimate as we did before, which is basically d minus, yes. Sorry, u, of course. This is what happens when you paste equations in your notes. Okay. Yeah, there are a lot of little typos in the notes. I've corrected many. I will send this version, well, after I correct these things, and that will be up on the website hopefully at some point. Okay. Good. So you can easily find out what sort of estimate of time in the future. It's just a time of order, a null time of order d minus 2 over theta inverse of 0. Sorry, it's very unreadable, but I think you know what I'm trying to say. Is the same conclusion as before. Null geodesics focus into the future, and these are the U geodesics. Okay. Now, we have the same problem that we've had before, which is that, all right, these equations tell us that some geodesics focus. Is this the end of the world? Is something really bad happening, or are these bad coordinates? And that's what Penrose addressed. But before we get to that, let's notice the thing we've been sort of ignoring for a while, but though I mentioned it, and now let's draw a diagram. So this is my d minus 2 dimensional surface. S, I cannot call this an initial value surface, it's codimension 2, not 1, and it has two null directions coming out of it, and one of them is u, and in my pictures u goes to the right, and we've just said that the U geodesics focus in the future if this expansion is negative. Now, in the time-like case, we took actually this expansion to be positive because it's the Hubble constant, the local version of the Hubble constant, and so we ran this backwards to show that the focus is in the past. But here we are actually interested in things that focus in the future, so we will keep it as it is, and theta inverse will be negative, so these will focus in the future. The question is, what happens to the V geodesics? It is, so now you might guess, yeah, so if theta, so I need some notation actually, which I might not even have in my notes. Yeah, I've used some other notation. So I guess I should have defined theta u. It's not a component, it's the u expansion. So if theta u is less than 0, then this figure is true. And the question is, what is theta of v? Now, it could be that theta of v is greater than 0, in which case the V geodesics focus in the past. This is one option. And I'll show you that this is a kind of default option. This is a very standard thing that's realized in ordinary surfaces. Okay, so under these conditions, the U geodesics focus in the future, the V geodesics focus in the past. Okay, but there's another possible set of conditions, theta u less than 0 and theta v also less than 0, in which case the picture is different. The U geodesics focus in the future and the V geodesics also focus in the future. There are two more possibilities, which are the time reverse of these two, but that's not interesting. You could have both these being positive, then both sets will focus in the past, You could have reversed the role of u and v, then you will reverse the role of these two. But invariantly, this is different from that. We can imagine a surface where the initial conditions are such that geodesics, one set of null geodesics focuses in the future, the other in the past. But we can also imagine a surface which has the property that both sets of null geodesics focus in the future. And this is very important. I claim that this is normal behavior and this is somewhat pathological, but if you have experienced some black hole physics, you will know that this is exactly what happens in known examples of black holes, and Penrose basically made his theory about this situation. So this kind of surface which does this is called a trapped surface. So I'll discuss what's a trapped surface after the tea break, but let me just give you a little example from simple geometries. So a nice example which again reminds us of the difference between space and space-time is when I take t this way, x this way, and let's take y here, and let's just forget about z. So we are in 2 plus 1d Minkowski space-time. Let's take a circle in the xy plane. This is meant to be a horizontal circus in the circle in the X circus. I've been too often to Oxford Circus, I think. It's in the XY plane. And now what I'll do is to define my coordinates such that, so first of all, what's the metric on this? So this is, first of all, it's 1D. So it's D minus 2 dimensional. It satisfies the conditions of this surface, of this these transverse coordinates to the null directions. Remember, there were xa's and there were d minus 2 of them. So here d is 3, so there's only 1, and that coordinate is an angle. This is compact. And ds squared, as we know very well, is r squared d theta squared, where theta is the coordinate on this. So what's r? Well, I have u equals t plus r and v equals t minus r. And I've lost where it is, so again I'm not sure if it's plus or minus. U is t plus r and v is t minus r. And so this metric is actually a quarter u minus v squared d theta squared. Okay, now with this, the determinant, the square root of the determinant, which I called which I didn't call anything, just root det g, is just half u minus v. Okay, so now what's the expansion on this surface? This null expansion, well, we have del UA is positive and del VA is negative. Del UA is half and del VA is minus a half. So they're of opposite signs. And this perfectly fits our intuition because this says that the null geodesics in one direction, in the radial direction outward, and the radial direction inward, some will focus and some won't. And it's pretty obvious in space that if I have a null geodesic that's going out from here, outward from here like that, then they will actually spread. But if they're going inward, then they'll actually focus. Okay, so there's one direction where they focus in the future and one direction where they focus in the past. That's what this is saying. So it's exactly that, right? Because theta is del UA divided by A. So we've just shown an example. Okay, it's the reverse of those signs, but just because I took one sign of this square root, but it's one of each. And that's natural. Basically what you're saying is I have a circle, or more generally a sphere. The ingoing geodesics will focus because they're ingoing, there isn't that much space inside, they're all pointing towards each other when going in. So if they're going into the future, they will focus. If they're going out into the future, they will not focus. So this is natural, this one. This is the one that's very hard to find, and I think this is a good point to break for tea, and then we'll come back and try to see what can be said about this case. which will require some rigorous definitions and a little bit of topology, and we'll have a Penrose's theorem. Good? Okay. Okay, so now I'm going to discuss, to define this concept called a trapped surface, and we're going to be discussing it for the rest of this lecture. So it's a compact d minus 2-dimensional space-like submanifold called S of the full spacetime, such that both its null expansions, theta u and theta v, are negative everywhere on S. Then it's a trapped surface. So compact is a new feature that we hadn't really assigned to our hypersurfaces previously, at least not always, but for this theorem it has to be. D minus 2-dimensional is natural because that's what has two null expansions, and it's space-like. That's also natural. We've just gone into a discussion this morning about how you naturally have space-like submanifolds which are orthogonal to null directions. And so that's what you call a trapped surface. And what we managed to show so far is that a circle or in Minkowski, or a sphere in Minkowski, is not a trapped surface because it has one positive and one negative. So we haven't found any yet, but it doesn't mean they couldn't exist. However, we'll now state, so one could of course easily continue from here by showing you that there is such a thing in the metric of a Schwarzschild black hole, but instead I'll state Penrose's theorem, and then if we have time, and I'll discuss its proof, which is a little involved, and then if we have time, we'll talk about the example. So let M be a globally hyperbolic space-time. So these words are back. This means that they have a Cauchy hypersurface, or it means that the space of curves from a point to another point is compact, or it means the causal diamond of any pair of points is compact. So let's assume this, and let's assume that it has a non-compact Cauchy hypersurface. Now this may look a little artificial. Why are we putting this restriction in? But I'll just tell you in a second why it's natural from his point of view. So let's call this that hypersurface sigma, and satisfying the null energy condition. That is, of course, essential, otherwise we don't get focusing in the first place. Then if M contains a trapped surface, then it is not geodesically complete. And as we've discussed many times before, not geodesically complete is the modern politically correct, polite way of saying singularity. But it's actually it's more correct. And actually, in this case, one difference is that in the Hawking example, in his first theorem, which I discussed here, all geodesics to the past had focused by a particular time. But that's not necessary. That it of course makes the space-time very geodesically incomplete. But it's enough if one geodesic doesn't extend. So it's actually just one geodesic. You just prove that one geodesic is incomplete, and you're done. So now we have to prove it. So first, why non-compact? Well, it so happens that Minkowski spacetime doesn't admit a non-compact Cauchy hypersurface, and that's pretty obvious from the geometry. It's just Euclidean space and then time. And the simplest Cauchy hypersurface we can think of is in usual Cartesian coordinates, just t equals 0. So just the Euclidean space at time 0. And to be Cauchy, it has to cover all of Euclidean space at time 0. If it's going to end or be compact or be spherical or something, then there'll be always some geodesic that will not land on it, and then it won't be Cauchy. So it has to be so the Cauchy hypersurface is non-compact for Minkowski, but more generally it's non-compact for all asymptotically flat spacetimes. So this is true for asymptotically flat. And I guess in the 60s and actually up until more recently also, it was thought that our spacetime might be asymptotically flat, and so this is then, you know, the black holes we study and the ones that were known in Penrose's time, Schwarzschild and so on, are all asymptotically flat black holes. So it's a very natural restriction. So it is not that restrictive. However, if you want to run these theorems through for ADS or DS, you just need to start again. I'm not enough of an expert in the field to tell you where you would reach, but my point is that these theorems simply do not apply. So one has to, their methods might apply, but the theorems as they stand don't apply to those cases. Okay. Now, what's the strategy? So the strategy is to and in this strategy will employ a number of things that I introduced over the course of these lectures in a useful way. So again, I call my surface S, so let me draw it. So this is my putative trapped surface, and what I'm going to consider is J plus of S. So I told you that for any subset of space-time, I can always find J plus of the whole set by simply taking the union of the causal future of every point in the set. So I'm going to consider J plus of S. Its dimension, so S has dimension D minus 2. So J plus of S has dimension D minus 1. Okay, the same dimension as a Cauchy hypersurface, except that it's null. So it has, if you like, it has the D minus 2. So we're talking of this interior here is J plus along with its boundary. And so we have everywhere we have D minus 2 coordinates which tell me where I am on S, and then one more coordinate which tells me where I am above, which could be along U or V, because both directions take me into the future. So it's just the complete causal future of S. So we want to prove some properties of J plus. So it's a D minus 1 dimensional null hypersurface. Hypersurface always means it's codimension 1, and null means that it contains a null direction, and that's pretty obvious from the drawing. Okay.
You mean Raychaudhuri or boundary?
No, sorry, sorry. Excuse me. I have said things about J plus and other things about boundary of J plus. So it is the, yeah, excuse me, I thank you for correcting that. J plus is that, including its boundary, but del J plus, the boundary, is the one that's D minus 1 dimensional. So the causal future of any set, even of a point, has the same dimension as space-time, because it's the set of all space-time points I can reach by causal curves, and so that's always D-dimensional. It's just not the full manifold, but the boundary del J plus of S is the D minus 1 dimensional null hypersurface, and we are going to show a few properties of it. So del J plus of S is achronal. It's not very hard. 2 del J plus of S is in fact compact. Now, if you are willing to believe these two, then we're actually done and we can even leave. So everything is about proving these, or at least arguing for them. Because once this is done, what is our logic? Well, so if you remember, when we talked about Cauchy hypersurfaces, we noted that different Cauchy hypersurfaces, because they had this property that every inextendable time-like geodesic passes through each of them, there's like a one-to-one correspondence between sigma and sigma prime, which endows all sigmas with the same topology. Now, there's a corollary of that theorem, which probably I should have stated then, which says, so this drawing says that any Cauchy hypersurface, CHS, is topologically, so the correct word is homeomorphic, which means topologically equivalent to any other. That's a result I did mention, but there's a corollary which says that any achronal hypersurface is again topologically equivalent to part of a Cauchy hypersurface. So this is the theorem and this is the corollary. So in this one, we are not saying it's a Cauchy hypersurface because it is not space-like. It's not everywhere space-like. It's in fact null in part of it, but it's still topologically equivalent to part of a Cauchy hypersurface. But once we've proved that this is compact, and we've also got that the Cauchy hypersurface is non-compact, we have a contradiction. And the proof of these two properties relies on the globally hyperbolic nature of space-time. So if we find a contradiction, it means that one of the assumptions was wrong, and in this case the only assumption essentially was the globally hyperbolic nature. And that's the theorem. So we have to prove that global hyperbolicity implies these properties, and then this topological equivalence says, well, del J plus is compact, but the Cauchy surface is non-compact, and therefore this isn't being satisfied, and therefore the space-time has to be geodesically incomplete. I'll admit it's a little bit of a, what's the word? It feels a little bit of a kind of disappointment at the end. It seems to rely on something very, very topological, but that's what it is actually. Okay, good. So I'll run you through a simplified proof of these properties, and in fact this proof goes through for any compact set K. So I'll call it K, and I've called it that in my notes. It doesn't even have to be D minus 2 dimensional, but has to be compact. So we'll have three results about compact K and its causal future, and again I'll be interested in J plus of K and the boundary del J plus of K. And in order to use it, we'll simply plug in that K is our D minus 2 dimensional trapped surface S. Okay, good. Of course, this and trapped surface we need to use the existence of a trapped surface, without which obviously we can't conclude anything. Okay, so there are 3 steps in the proof. So let me, I don't know if I should keep this to remind us what we are trying to do. Maybe I'll just erase this. There are 3 steps. One of them, which I think is relatively simple, is that J plus of K and its boundary are both closed, which means that in this topology they contain their limit points. Okay. 2, which will follow, is that this is achronal. Okay, so right now I'm actually only going to use globally hyperbolic, and I won't use trapped because I haven't, K need not be trapped, K is just anything. This is always true. The trapped part will come later. And then del J plus of K is a manifold, so it satisfies the conditions to be a differentiable manifold, though not always smoothly embedded. Though this looks a little technical, it's actually the easiest. Well, part of it is easy to argue. Let's go in order. Okay. So, to show that J plus is closed, we need to consider a sequence of points. So, maybe it will help if I draw them here. Consider a sequence of points Qi. So, Q1, Q2, and these points sort of get closer and closer, and they're supposed to converge to a point Q. And what we want to argue is that if they do converge to a point Q in the space-time, that point Q is still in J plus. Okay, they can't converge to a point Q that's outside J plus. That's what closed means. And the proof is actually really beautiful, and I can just draw it here. I simply draw a causal curve from K to every one of these points. Okay, through every one of these points. And yeah. Now this family will converge by the theorem we proved earlier to a causal curve, which must end at the point Q, because each of these curves passes through a point, and the set of points have been designed to converge to the point Q. Now each of these curves converges to a curve, and the compactness of the space of curves says that that curve is entirely in my J plus. Okay, and that being so, so it must pass through Q, and since Q is a point on a curve and that curve is in J plus, Q is in fact the limit point of these Qi, and it's in J plus, so J plus is closed. More details are in my notes, and still more details are in Wald's book or Witten's notes. So that's step 1. Step 2 is in a way simpler. We don't need to use, so here we used compactness of the space of curves, and that's, as we remember, a consequence of being globally hyperbolic. So that was always used. And that's the thing that's going to fail at the end. Okay, for boundary, it's even simpler. We consider a sequence of points, let's say here, R1, R2. And the question is whether R is also in the boundary, its limit. So the only other option is that R is somehow gone inside, and this topologically is ruled out. So can R be here, the limit of these? in that case this boundary would not be compact. But if the limit point R is inside here, then there's a neighborhood by definition of limit point which is fully contained in J plus and doesn't intersect the boundary. Okay, that's part of the definition of a boundary. Now we have a sequence that converges to R, but R is inside a neighborhood, however small, which is fully distinct from the boundary. That means that in this sequence R1, R2, there must be some n such that Rn has started being there. Okay, there's no way they can terminate there unless some of the later R's in this set of points are already inside this neighborhood. And that's not possible because I started taking my R's all on the boundary. It's actually a relatively simple fact that, you know, when you have a limit of things in a subspace, then the limit also stays in that subspace. So this proves the second thing, that boundary of J plus is closed. And so part 1 of our theorem is done. Achronal. So yeah, it's almost the same proof as for prompt geodesics. So we want to show that this thing, del J plus of K, is achronal. So supposing it's not, then of course there's a time-like path connecting 2 points. Okay. Now this path is definitely not prompt. So there's a shadow path which gets there earlier. But actually, so let's say this point is P and Q. So now there should be a shadow point that gets there earlier, but that means that Q cannot be in the boundary in the first place. Okay, because a prompt path has to end in a point on the boundary, but a non-prompt path has to end at a point on the bulk. We showed that. Okay, so this shows the achronality of the boundary of J plus of K. And the third one, I'm not going to go into the details, but just to give you an example, imagine K was just a single point. Then the boundary of J plus in Minkowski, then the boundary is just a cone. A cone is a manifold, but it has a singular point. So it's not smoothly embedded. So one has to have that caveat. Otherwise, it's reasonable to imagine that the boundary of J plus is a manifold. Okay. So 3 things that we wanted to prove, at least this one we stated, and these 2 we gave some argument. Any questions about these? They do require the same sort of arguments over and over. That's the only consolation I can offer. That once you sort of get used to them, they're pretty much the same arguments.
Sorry, why is that manifold?
No, so it's not smoothly embedded in space-time. That's what it. Yeah. Yeah. This I don't understand, to be honest. The statement is precisely that it's a manifold, though not smoothly embedded.
Right, it could be a manifold with a coordinate. So, for example, we have a cone and it's a coordinate. That's not a manifold. Well, the same thing for a manifold. Okay.
Yeah, so.
Manifold everywhere.
Yeah, this here the boundary has a sort of a boundary, which is not something a smooth manifold can have.
Yeah.
You're right. You're right. I must admit I don't fully understand the content or relevance of this. Okay. Okay. Good. Okay, now the last thing then we need to prove is what we set out. So this was one of the 2 things I said was needed for Penrose's theorem to apply, and the other was compactness, and we are almost there. We've proved it's closed. So now we want to just show that del J plus is compact. And now actually we are going to make this a trap surface. So up to now the theorems were true in general for general Ks. Now this will be actually our S, which is trapped. And it's this which renders the boundary of J plus to be compact. Okay. So, so there's a small lemma. Um, consider a prompt geodesic from a point here to some point, from any point in S to some point Q. Let's us, and this is gamma, and let's consider that it's prompt. Okay. Now, good. Now, we already know that this is trapped. So, this is a null geodesic. That means it would have focused. So, let's assume that it has focused and we are trying to continue to a point beyond its focal point. Good. So, let me call this point Q. Let me call the point where it starts P. And okay, this drawing is not very good because it's a little difficult to draw because we are working with the causal future of an entire set. And so, um, so this is a bit tricky because I want to start at an arbitrary point in S, but then I want to end, for example, at I want this to be prompt initially. So, do you understand my difficulty in drawing it? I mean, if it's a point here, this is not the boundary of its causal future, but to be prompt, it really has to go from here to a point on the boundary. Okay, so another way of saying it is that, okay, I don't know how to say it any better. My problem is in drawing it. So I can state the theorem, but I may not be able to draw it. So let me write the words. I think that will be easier. Then maybe you can help me draw it. So consider a geodesic from null geodesic, of course, from P in S to a focal point Q in J plus of S and beyond. Now, this cannot be prompt once it goes beyond. We proved this last time. This is what fails after you cross a focal point. But there's an initial segment which is prompt. So let's call this geodesic gamma from P in S to a focal point and beyond. And the initial segment gamma PQ is prompt. So this is a theorem we also argued for earlier today and last time, that even if you have any null geodesic, its initial segment is prompt. It's only after that that it becomes non-prompt. Okay. Now this gamma PQ is prompt and it's also compact as a set of points, because what is it? It's just a closed interval. It's a curve that starts here, ends somewhere, includes both its endpoints and all points along it. So on its own, it's compact in the topology on this manifold. Okay. So now consider the intersection of gamma, the whole geodesic. So focal point, continue beyond it. Here's Q, here's P, and we continue beyond. So the whole thing is gamma, while this segment is gamma PQ, just the first segment. Good. So now consider the intersection of gamma with J plus of S. or actually with the boundary of J plus of S. Then lemma, this is compact. So gamma is, this is compact. So gamma is compact. In fact, all of gamma is compact because it's just a set of points from beginning to end. So that's compact. And the lemma says that this intersection is compact. So we are going to basically, this is what we want to prove is compact. We are going to prove that the intersection of any geodesic, even beyond its focal point, with this boundary is compact. And then we extend it over all geodesics and we get our result. Okay. So yeah. So the key result is that gamma intersection boundary of J plus of S is in gamma PQ. Namely, only its initial segment is prompt. So this is the only segment that can intersect with the boundary of J plus. This part is non-prompt, so it can't. Okay. So this intersection is contained in gamma PQ, and it's a closed subset of, as a closed subset. Again, it includes its endpoints. Because we already showed that this boundary is closed. Okay, so this intersection is contained in gamma PQ as a closed subset, and gamma PQ is compact. Well, the whole of gamma is compact, but we only need the fact that gamma PQ is compact, and therefore this is true. Gamma intersection del J plus of S is compact. That was the lemma we're trying to prove. So the steps were the following. We have a curve gamma, which itself is compact. We have del J plus, about which we don't know what it is. The intersection has to be contained in a segment of the original curve. The segment of the original curve is compact, therefore the intersection is compact. So that's step one. Now we repeat this for every point in every point Q in the boundary of J plus. So we repeat it for all curves which go to the same focal point and continue after that. Okay, and every such intersection of gamma with boundary of J plus will be compact. But we already showed that boundary of J plus is achronal. Okay, so sorry, before that, then repeat this. Good. This is the last step. So repeat for all curves gamma. Now I didn't say maybe, but these gammas are all taken in the u direction. Okay, but we could have taken these gammas in the v direction. They're two independent null geodesics, and now we are using the fact that both focus in the future. Okay, so first we repeat for all curves gamma in the u direction. We've done it for one, and then we repeat for all curves gamma in the v direction. And what you see is that all curves in the u direction and all curves in the v direction, starting at all points of this manifold, spans the whole of this thing, and therefore the intersection of all such curves with del J plus will tell me that del J plus itself is compact. That is, if the intersection of all such curves with del J plus is compact, then that's enough information to argue that del J plus is compact. And that's sort of the hard part of the theorem, is to prove that with focusing of both curves in both directions in the future, del J plus is compact. And notice that if that didn't happen, if these didn't focus, we wouldn't have these arguments about a non-prompt geodesic whose initial part is prompt, and we wouldn't be able to argue that all possible curves to the future intersection with del J plus are compact. It's that argument which finally gives this, and now there's nothing to do because, as I told you, if this is compact and achronal, which we proved, it's supposed to be homeomorphic to a part of the Cauchy hypersurface, but that's non-compact and so it's not possible. So if you want a one-line summary, it says the presence of a trapped surface having focal points in the future allows me to argue for the compactness of the boundary of the causal future of the trapped surface. That's the one-line summary. And that proves Penrose's theorem. Okay. Now, I don't have too much more to say that can be said in a short time. So actually, I'm going to essentially end in 5 minutes, but we can have discussion or questions if people want. You probably have already seen this famous diagram where actually the diagram is from Penrose's own paper and it's reproduced a million times. So this diagram is a shell of collapsing matter represented as shrinking circles going forward in time. And at some point a trapped surface forms. Now we draw the light cones like this. And at some point a trapped surface forms. So that's here. This is the trapped surface. In Penrose's paper, it's, I think, in some sort of boldface. And then here you have the singularity. And here you basically have the black hole. So once you form a trapped surface, you are inevitably inside the horizon. This is where the horizon forms. And you've probably seen this diagram that if I draw a local light cone here, far away from this horizon, it just looks like that. And when I get here, it sort of starts to tip over. But when I'm here, it's actually done this. And then when I'm inside, it's actually like this. And this is just the effect of the Schwarzschild metric. It's a very well-known drawing. And the key point is that here you have the option to go that way, which means you're escaping from the black hole, or to go that way, which means you're going towards the black hole. Here you still have that option, but it starts to become harder to escape. On the horizon, one null direction takes you in, but one null direction takes you parallel to the horizon. So you stay on the horizon forever. And once you're actually inside, both null directions point inside. And that's exactly the property, the feature of the closed trapped surface. So this formalism is basically the formal way to explain that this generally happens, and that the time at which the trapped surface is formed is sort of when you know that you are destined to form a black hole. And okay, it's true that to form a trapped surface you might need some approximate amount of symmetry, but once you formed it, any perturbation that you might try to make on it is not going to affect anything, because then the arguments going forward in time are topological. So the singularity, so there will be a singularity, the space-time will be geodesically incomplete, and it goes beyond what was known at that time, which was that in Schwarzschild solution this happens. And this is just a factor of one solution, which was the most simple and spherically symmetric solution. And as I told you, Lifshitz and Kalatnikov had sort of poo-pooed the idea that all these singularity theorems could actually be true without symmetry. Their view was that they're highly symmetric situations, and that's why you're seeing singularities. And this 3.5-page paper changed all that by arguing that this is the only requirement. Once you have a trapped surface, you're doomed. And the Nobel citation for Penrose actually emphasizes that he sort of gave the argument why black hole formation is a generic and not very special process, and ultimately that's why the universe is full of black holes. Otherwise, you might have expected one to form or none to form because some very, very special initial conditions were needed, which may not have been realized. But in fact, billions or millions or billions have formed. So, yeah, that's the result of this. So, in my notes, I have more detail about the how the Schwarzschild solution exactly fits, what is the closed trapped surface, how you see it in suitable coordinates, what is the story for generic black holes, what is then Hawking's area theorem follows. So that also has to do with geodesic expansion, but in a context slightly changed from this, but it's the same formulae. And then from all this, how black hole thermodynamics arises. So that's all in the notes. And beyond that, of course, in Witten's light rays, singularities, and so on, that review article, there's also the connection to quantum entanglement, which is a whole direction, and probably it is the direction which inspired him to get working on this. And yeah, I'll stop there. Thank you. Questions?
So this three-page paper included an awful lot of existing material.
Yeah, and of course, you know, there was, so the history is that Penrose wrote this very short paper, and in 65 or 64 or 65, and then Hawking was inspired by that to think about the time-like case, which actually turned out somewhat simpler. So he didn't need the null Raychaudhuri equation, just needed the ordinary one. So basically Hawking's thinking, as I read it, is, well, he's done all this with null geodesics. Why can't we revisit the original problem of Raychaudhuri and use global hyperbolicity to just come to a solid conclusion? But then by 1970, Hawking and Penrose joined forces and wrote a series of papers which I think for them had the full story. And then I think the Hawking-Ellis textbook is a distillation of a lot of that material. And then Wald is a distillation, but making some of the geometric arguments much more explicit. I mean, Wald is seen as a very heavy-duty book, but I think in a way Hawking-Ellis is more heavy-duty because they don't prove that much. They just leave it to you to figure it out. Wald, at least, you know, everything he says, he proves over many pages. And then I think Witten tried to distill that further and had this very nice novel idea about promptness, which somehow could recast things in a way that we can understand better. I think for me, at least, promptness was a real kind of, yeah, it was a bit of a jolt to understand it in this way. The achronal is a very dry and boring condition.
How much of this can you see in curve?
Yeah, how much can you see in curve? This is limited by the fact that I don't know very much about curve, to be honest. I guess the question is, first of all, whether it's globally hyperbolic. And certainly Reissner-Nordstrom, I think the extended one is not. And yeah, anything which has closed time-like curves is not globally hyperbolic. Yeah. So then one has to probably think about, you know, whether we can have restricted geometries, can restrict it. So the nice thing about global hyperbolicity is you can pick any hypersurface that you like, call it your Cauchy hypersurface, and then define its causal future and past to be the globally hyperbolic manifold. So it allows you to cut out a manifold by just, you can pick a surface and then say whatever is in its future and past, that's my manifold. If something in your manifold wasn't in the future or past of my Cauchy surface, too bad, I'm cutting it out. So you can chop off parts of a manifold, and this ties in with the concept of maximal extension. So we keep trying to extend a manifold, but one might say the Kerr solution or Reissner-Nordstrom are extended so far that they fail to be globally hyperbolic. So we shouldn't have extended them. So we should unextend them or restrict them to some part which is globally hyperbolic. Then these statements would hold.
And in that context, does the Cauchy horizons, show up in this?
Yeah, absolutely. So that's a whole discussion, and that's sort of the point that, if if you pick a Cauchy surface that has a horizon, then that's where your manifold gets cut off, and then it has a horizon. Some of that is in the notes. Cauchy horizon is defined, and examples are given. I don't know if I did this example in my lectures now, I can't remember, but there's this Garrosh example of just Minkowski with this hyperboloid trying to be a Cauchy hypersurface. And it fails because all future directed geodesic causal paths from this thing are contained in only in this wedge. They can never get there. And so you have this as your, oh sorry, I said it the wrong way. That's not the point. The point is that anything that's here has the opportunity to escape hitting the Cauchy hypersurface, because if you continue it back, it could remain to the other side of this past light cone. So a Cauchy hypersurface is defined by having any past directed geodesic of the manifold intersect it, and here, or just curve, and here you can find a past directed curve. It's perfectly time-like everywhere. Here it starts to become null-ish, but it's still time-like, and it's never going to cross this light cone. So this shaded thing is the Cauchy horizon. Now, everything below this Cauchy horizon is globally hyperbolic with respect to this Cauchy surface. So this is how you can restrict a manifold to be globally hyperbolic with respect to any Cauchy surface you like. How this would work in Kerr or Reissner-Nordstrom, I can't speculate, but it certainly should be worked out. Must have been worked out. Okay.
So how does this help the producers in Hollywood or Bollywood about making movies about when you get crunched?
Crunched, yeah. I mean, yes, actually, a good point. I should suggest it to them.
Reissner-Nordstrom has this timeline figured out.
Mm-hmm.
So basically, all you have to do is just make sure that you have some momentum using around it.
That's right. So, okay. Any other questions? Yeah.
We have like focal point starting from this Raychaudhuri, Raychaudhuri equation. You use the fact that the PUU component is positive,
yes,
right, which is null energy condition.
That's
but
right.
Actually, when you're deriving the equation for theta inverse, you are integrating over like some point from u equal to 0 to some u value. So you are roughly using like a average null energy condition instead of null energy condition. Obviously,
yes,
null energy condition implies
of course, and not the other way. Absolutely, absolutely.
So
that's correct.
The question is like, is it necessary to have null energy condition or average null energy
yeah.
condition?
No, so I think a lot of research done post these original papers, there have been so many papers of Hawking in that short period, 65, 66, 67. Many of them were trying to actually go beyond the assumptions, the original assumptions, because, they proved some result with some assumptions. Then they said, let's one by one demolish each of these assumptions. What if it's not global hyperbolic? Maybe it's something else. Strongly causal. What if it's, as you said, maybe in the null energy condition doesn't hold pointwise, but on average or in some other form. There are also several energy conditions. So all this certainly is in the literature. I probably can't say much about it.